In this section of chapter 15, we will define chemical equilibrium, equilibrium constant, Q values, and Le Chatelier's principle. Now, in order to explain and go over chemical equilibrium, I would like to begin with a simple analogy. Say we have reactants. We add it together. Initially, there will be no product formation, but as time goes on, there will be product build-up. So in this case, each person on this left-hand side would represent a reactant. As soon as it comes to this side, its identity gets changed. As you can see that it gets changed. The next one goes out over there, identity gets changed. That means it formed products. After some time, if one goes to the right, the one goes backward. And that's equilibrium. Now the question is, would there be any more changes in number at that point? Answer is no. The number is going to remain the same even though there is a forward and backward movement of all these reagents. Now same thing happens in a chemical reaction. At the beginning you'd have all reactants, then as you form products, after some time some products would go backward. And it would happen at the same rate the forward process happens. So forward and reverse process would be equal. So that's why we say that here these are the criteria for equilibrium. Concentration of reactants and products do not change with time. Forward rate equals to reverse rate. And law of mass action applies. We are going to explain to you what law of mass action. Here you see application of law of mass action. So when equilibrium is reached, that means after some time when forward reaction is equal to reverse reaction, there will be no more changes in concentration. Remember, at the beginning, reactant concentrations will go down and then product concentrations will go up. At equilibrium, since forward rate and reverse rate would be the same at that point, so there will be no change in the number of in the concentration of reactants or products. At that point, we apply law of mass action that tells us that if you have product concentration on the top, raised to the power, coefficient of balanced reaction, this 2 is coming from here. Reactant concentration on the bottom, raised to the power coefficient for nitrogen coefficient is 1, raised to the power 1, which is same number, and hydrogen concentration raised to the power 3, which is also coefficient of the balanced reaction. So law of mass action tells us that this value of equilibrium constant is going to be fixed as long as temperature is fixed. Now there are more than one type of units that we use for equilibrium constant. One is Kc when you have concentration or molarity units. The other one Kp when pressure units are used. Pressure units means atmosphere. The relationship between Kp and Kc is the following. Kp equals to Kc RT raised to the power delta N. Now delta N is actually products minus reactants. For the above reactions, if you look at this reaction, we have two products, 2NH3, minus 4 reactants, 1 nitrogen and 3 hydrogens is 4. So delta N is going to be minus 2. And that's what we need to use in this expression. For from reaction to reaction, this may change. R value is a constant, 0.0821 liter atmosphere per degree Kelvin per mole. And temperature has to be in Kelvin. Now here you see one heterogeneous equilibrium. What is heterogeneous? Say solid is mixed with a gas or liquid is mixed with a gas and they don't mix with each other. And when they don't mix with each other, that makes heterogeneous. we define equilibrium constant a little differently. First, you write down exactly like homogeneous equilibrium. So product concentration on the top. Here you have calcium oxide, carbon dioxide. Initially, you don't worry about which one is solid and which one is gas and which one is liquid. So let's write down calcium oxide is the solid, oxygen, carbon dioxide is the gas, G. Calcium carbonate is solid. Now, for solid, as long as even a little bit of solid is there, moles per liter is going to remain the same. So that's why solid concentration doesn't go into the expression. In other words, even though we originally wrote it down, this solid and this solid, there'll be no more changes, not at all any change in concentration, because the way we define concentration is moles per liter, and it doesn't change for any solid. So basically ignore that and consider it to be part of a definition of equilibrium constant. So only thing that goes in the K equilibrium or equilibrium constant is, in this case, carbon dioxide, which is gas, and that pressure changes as the reaction happens. So basically you need to remember that for pure solids and liquids, when mixed with a gas, you pretty much ignore solids and liquids or consider them to be one. That way you'd get the right expression. Now, large values of equilibrium constant means large concentration of products. In this case, you can better see it. If I have large value of equilibrium constant, that means I have large concentration of carbon dioxide. On the other hand, if equilibrium constant is small, that means I have a smaller amount of product. Now predicting the direction of reaction, what we call Q value. We already defined equilibrium constant. You must have product concentrations on the top, you can see, and raised to the power coefficients of the balanced reaction. That's how we got 2 on the top of ammonia, 1 on the top of nitrogen, and 3 on the top of hydrogen, because these are coefficients of balanced reaction. And keep in mind, these are the concentrations which exist after equilibrium is reached. Kc value is well known at 472 degrees centigrade for this particular reaction, which is 0.105. No matter what concentration you begin with, eventually the reaction would reach equilibrium and the value is going to be 0.105 for equilibrium constant at 472 degrees centigrade. As temperature changes, this number also changes. Now then, what is Q value? In equilibrium constant expression, all the values that you have are equilibrium values, not the initial values, rather the values at the end, after equilibrium has been reached. On the other hand, in Q definition, it's written down exactly the way we write down equilibrium constant expression. Product concentration on the top, raised to the power coefficient of balanced reaction, reactant concentration on the bottom, raised to the power, raised to the power of coefficient of balanced reaction. Same is the case with the other reactant. Now this is called reaction quotient because this could be any concentrations, not equilibrium concentration. And that's why Q value would change with time. On the other hand, equilibrium constant would not change once equilibrium is reached. However, Q value is going to change from the beginning until it reaches equilibrium. Now this allows us to predict how this reaction is going to proceed if Q value we begin with greater than equilibrium constant or less than equilibrium constant. But we know for sure that Q must change with time until it reaches the value of equilibrium constant or reaches equilibrium. Here we're giving a specific example when nitrogen concentration is 1 molar, hydrogen is 1 molar, ammonia is 2 molar. Remember, you would have product concentrations on the top. I think it would be helpful if I also write down this actual expression, which is on the other slide. So ammonia concentration raised to the power 2, nitrogen concentration raised to the power 1, hydrogen concentration raised to the power 3. That comes from the balanced reaction that you see here. Now, with all these numbers 1, 1, and 2, you're going to get 4. And that 4 is greater than equilibrium constant, which is 0.105. And let's assume that we are doing experiment at the same temperature at which Kc value is 0.105. So once Q value is large, it has to come down with time, because every system would go towards equilibrium. Every reaction would head towards equilibrium. So what that means is Q value must go down because it started with a larger value. As Q value is going down, ammonia concentration has to go down, and at the same time nitrogen and hydrogen concentration would go up. Okay, now what ammonia concentration goes down, what does that mean? Reaction can go in two ways. Left to the right. Let me show you with a different color. Reaction can happen from left to the right, that direction, or from right to the left. When I'm saying that product concentration is decreasing, that means some products are breaking down into reactant, going back to the reactant. And that's why ammonia concentration is going down. So Q value going down means reaction is favorably or more prominently happening from right to the left. So that's why reaction will be favored right to the left. So Q value tells us which direction of reaction will be favored. Let's try another example. In this case, I have nitrogen again 1, hydrogen is 1, ammonia is 0.10. If I calculate Q value exactly the way we got Q value in the previous case, ammonia concentration on the top raised to the power 2 because of the coefficient is 2, divided by nitrogen and hydrogen concentration and raised to the power coefficient of balanced reaction. In this case, I get 0.010, which is less than equilibrium constant. So Q value is less than 0.105. Now, in case it happens, Q value equals to Kc. So if you find that Q value equals to Kc, that means it's in equilibrium. That's the condition of equilibrium. So when Q value is not equal to Kc, then Q value has to change with time, so that eventually it reaches the value of Kc. So in this case, Q is less than Kc. What that means is, since it's less, it has to reach the value of Kc. It has to go up in value. So Q must increase with time, and Q, you already know the definition of Q. The top number in this case is the product, so it has to go up, means Q value going up means the top number has to go up. That means product concentration has to increase. Product concentration can only increase when reaction is happening favorably from left to the right, so this way. So more nitrogen and hydrogen are reacting to produce more of ammonia. So larger ammonia and a smaller amount of nitrogen and hydrogen would give a larger Q value. So Q value would keep on increasing with time until it reaches the value of Kc. So eventually it's going to reach the value of Kc. So whenever Q is less than Kc, Q value has to go up and reaction will be favored from left to the right. The state of equilibrium is comparable to a healthy person who is healthy and happy. So any kind of stress or headache that healthy person would get, he would not like it and would try to overcome that problem. So we all know that when you have a headache, you get medicine, say Tylenol, Advil, Similarly, if you have a stress, you try to get relief from that stress. Same is the case with a chemical equilibrium. Reaction to try to maintain its equilibrium. So whenever there is any kind of change, that change is considered to be a stress, and it would try to adjust itself so that the change has been minimized. Here we are defining Le Chatelier's principle that deals with how equilibrium would change when there is a change in concentrations, pressures, or heat involved in the equilibrium. So this is how Le Chatelier's principle is defined. When stress is applied to a system in equilibrium, changes take place in such a way so as to reduce the stress and restore equilibrium. Now let me explain this to you by going over problem number 61 from page 646. This reaction is given 2SO2 plus oxygen giving 2SO3 and heat. That means it's an exothermic reaction. Heat is given off. How do I know it's an exothermic reaction? Because delta H is negative. Delta H negative means heat is given off. Now part A. Say it was in equilibrium. You're adding oxygen. Remember, it doesn't like any change beyond its equilibrium value. So it maintained its equilibrium concentration of oxygen. Now you're adding extra oxygen, and it doesn't like it because it's pretty much like headache. When you're healthy, you're happy, and all of a sudden you got headache, so you try to get rid of that. Similarly, this extra oxygen would be like headache for this reaction. So to try to minimize that additional oxygen. Now remember that reaction can go in two ways. Left to the right, that means it can form more products by using up reactants, or it can go the other way. It can form more reactants by breaking down products. Now, when it wants to minimize the amount of oxygen, only one way it can go, which would be from left to the right. Because that's how you're making use of oxygen and minimize the amount of oxygen. So that's why I answered this. When oxygen is added, you're really increasing oxygen beyond its equilibrium value temporarily. Then reaction must go in a way that would reduce O2. And that, in other words, it should go from left to the right. Then, in other words, more oxygen is going to react and produce more SO3. The next factor that we're going to discuss would be application of heat. Say you're applying heat. Already the reaction generates heat because it's an exothermic reaction. So you get extra heat as a part of the reaction. Now you're adding some extra heat, and it doesn't like that extra beyond its equilibrium value. So it has to minimize the heat that you added. Again, reaction can go from left to the right or right to the left. But if it goes from right to the left, it makes use of the heat in running the reaction from right hand side to the left hand side. That means some products would break down by using that heat, and it would form more reactants. So in other words, in order to minimize heat, reaction has to go from right to the left. What would happen if volume is doubled? Think it this way. I have a reaction container with this volume, and I have a few of these reagents in here. All of a sudden I double the volume. So by doubling means I have made extra space for molecules. That's the change. That means density has fallen down. Whatever density it had in this small volume, by giving more room, that means its number density has gone down. Other way of looking at it would be you created extra space for molecules to get in. In other words, you need to have production of more molecules in the reaction. So that would be the natural trend. When volume is double, reaction would happen in such a direction so that overall number is increased. Now see which way the number is increased. Reactant side. If you think about reactant side, each time reaction happens, there'll be 3 molecules involved, 2 SO2 and 1 oxygen. Product side, you have 2 SO3. So each time from reactant to product you get, there's a number decrease from 3 to 2. On the other hand, if it goes from right hand side to the left hand side, there is an overall increase in number from 2 to 3. So whenever we need to fill in this empty space, let me show you with arrow, empty space with new molecules, reaction has to generate that extra molecule. So by going in which direction you'd have extra molecule or extra reagent, that would be from right to the left, because that's how you're increasing the number of reagents. This is the problem number 61D. So question is, what would happen when catalyst is added? Now, I mentioned before that when catalyst is added, it basically changes activation energy or energy barrier. So if the original barrier was like this, the final barrier would be smaller, so that reaction can happen faster. But reaction happening faster doesn't necessarily mean that there'll be any change in equilibrium constant. Actually, when reaction happens faster in both directions, from left to the right as well as right to the left. So overall, there'll be no effect on equilibrium, even the rates are going faster. It's like one person is going from left to the right at a fast pace, another person is going backward at a fast pace from right to the left. So there is overall no change in equilibrium concentration or equilibrium value. So catalyst doesn't change equilibrium, even though it enhances rate in most cases. Sometimes it can also decrease the rate. Now, what is going to happen if total pressure is increased by adding a noble gas? So noble gas is something has nothing to do with a reaction. That's what I mean. In the top reaction, you're adding another gas which has nothing to do with that reaction. So obviously, there'll be no effect. Now, this is comparable to someone else got headache, but you are all right. You're not going to take Tylenol. So in other words, you don't need to make any adjustment because someone else had headache. No. So that's why there'll be no effect on this reaction, even if you add a noble gas. Next question is, what is going to happen if SO3 is removed? SO3 is the product. So I'm removing some of the SO3 molecules from the equilibrium. So you're basically reducing equilibrium concentration of the product. So that means reaction has to produce more product. And it tells you that by going from left to the right this way, you can form more products. You can see sulfur dioxide is formed more if it happens, reaction happens more favorably from left to the right. And that's why the answer to this question is left to the right direction of reaction will be favored.